although the PowerPoint slides have been available on Mastering Chem, I haven't used them. I don't like PowerPoint that much because I like much less formal. I've been to hundreds of PowerPoint talks, and they're all kind of formal. It's hard to interrupt the flow of the PowerPoint. But they're, on the other hand, maybe it's much better than being a little too informal. And so you can let me know how this goes. But we're going to go for PowerPoint for the remaining chapters. All right, basically what we want is enthalpy, because we want to know the delta H values for these, whatever reaction process that we have. We'd like to know the delta H. Why? Well, we want to know the delta H because, one, most reactions are under, constant pressure or constant volume conditions. Constant pressure. Delta H is for constant pressure. So, and then, do we want to worry about the tax bonus or no tax, no bonus involved in reactions? Do we want to worry? No, we want the out the door price. When you go buy something, you want to figure out, how much is it going to cost me, to take it home, not how much it costs, pre-tax or whatever fees are associated with it. And so this is the out the door price. In fact, this is, we don't even have to worry about work. Work's already factored in, right? And so this is the net price of this. And so what is the net price? Well, actually, we're going to get 566 kilojoules of energy from this. We're going to get 566 kilojoules per mole of what? Now, this says per mole, but this is 2 moles of carbon monoxide, 1 mole of oxygen, 2 moles of CO2. And so what do they mean by per mole of reaction? Because we have different stoichiometric coefficients here. And so what they mean by per mole here is as the reaction is written. And so if I'm looking at carbon monoxide, this is the amount of energy that's going to be released. Is this? This is odd, but this is the amount of energy that's going to be released per 2 moles of CO, per 1 mole of O2, and per 2 moles of CO2. And so normally we don't write this per mole stuff here. Normally we would just write delta H is equal to minus 566 kilojoules for the reaction as written, and then look at each individual reactant and each individual product and do it per mole or per whatever moles there are in that stoichiometric coefficient. And so again, the way this reaction, the way this reaction is written here is odd, because here it would just be kilojoules. And so this is sucrose, or table sugar, and if we completely combust it, we'll form CO2 and water. Well, we're going to get 5,650 kilojoules if we combust 1 mole of sucrose with 12 moles of O2, producing 12 moles of CO2 and 1 mole. And so this per mole is deceptive. It should just be kilojoules here. Now, if I want to do it per mole, then I would do per mole of sucrose per 12 moles of O2. So I could do it as an individual conversion factor during that. And so let's say I had 30 grams of O2 react completely. If I had 30 grams of O2, I could convert that into moles. From moles of O2, I can go to kilojoules based on this, assuming that the reaction occurred and all 30 grams were consumed by using this as a conversion factor, but this would be this many kilojoules per 12 moles of O2, not per single mole of O2. So that's normally how these are written, and Petrucci writes it like this, except in the slide he didn't, but different people have made these slides. Physical significance of enthalpy change. So what does delta H represent? Well, delta H represents, it's not just heat. Does it have to be heat? I talked about this the other day. The work we can't avoid. This is the P delta V work, right? But the heat, okay, if you have the P delta V work, then the rest is heat, because delta, as we recall, here, I'll write this on the board maybe. Delta U is equal to Q plus W. And so it's the heat in the sense that, you know, after we subtract out the work or add in the work or whatever we do with the work, this is what's left over, and that's what we call the heat. But we could actually convert some of that change in total energy into more work if we wanted. And so this you know, I don't always call it the heat, you know, under normal, because we don't always have to convert that into heat per se. I mean, this change in potential energy can be converted into other forms of work, like electrical work, mechanical work, etc. And so what I like to refer to this is the net energy we're going to get, you know, after we subtract out the natural work of a chemical reaction. All right, there's no simple physical or molecular interpretation, meaning that simple physical or molecular interpretation, meaning that, you know, if we're to calculate the absolute enthalpies, right, we have difficulty in the sense that we don't. Delta H is not equal to H final, excuse me, minus H initial. Anyway, this is the QP term. That's our definition of delta H. There's one more restriction here, and that's not shown on this slide. What is the additional restriction? Okay. This P means what? Constant pressure. Well, that's written here, but there's something else. Represents the heat transferred under constant pressure conditions, and 2, temperature is constant. We normally, you know, it's tricky because temperature, this is a state function. And so temperature doesn't have to be constant, it just has to go back to the same temperature that it was initially. And so the temperature could change and then go back. And so in terms of state function, yeah, the temperature is constant in terms of state function because all we look at is the final and the initial. We don't look at the path, but during the path, temperature can change. There's something else, though, that we have to factor in. So 1, delta H is equal to QP if the pressure is constant, and 2, there's one more restriction. What is that? Remember, we're factoring in the tax. And the tax, if you factor in the tax, does the tax change from state to state? Yeah, the tax changes. You can't use California state tax for Oregon, right? Oregon doesn't have a state tax. And so what we have to do is we have to figure out what the tax is, and the tax is going to be fixed at what kind of tax are we dealing with only? The natural work, P delta V work. And so the other restriction is the work is equal to P minus delta V work only. And so that's missing from this slide, but you can add that in. This is slide number 7. And so that's good because if everything's on the slide, then you don't have to do anything, which means that it's harder to remember. But add that to slide 7. It's missing. All right, now we have processes too. You know, processes and reactions are treated the same. The initial temperature and the final temperature is the same. And so here, there's a change in enthalpy. The initial temperature is this, the final temperature is that. In fact, in this change, the temperature is constant because this is called boiling or vaporization. You know, water boils at 100, oh, this is at 298.15. Sorry. This is evaporation, you know, because water doesn't boil at room temperature, does it? And so we have evaporation, and it's going to cost you 44 kilojoules per mole for evaporating water. Here, melting ice. Melting ice occurs at 0 degrees C, so this is correct. And this is going to cost you 6.01 kilojoules. Notice, you know, to vaporize water costs a lot more energy than just to melt it. Because when you melt ice, you know, you don't completely break the hydrogen bonds. You form liquid water, and the hydrogen bonds are still intact. And so, these are just 2 processes, and these are the delta H's. You don't have to memorize these. But in biochem, you know, they have a whole chapter talking about things like this, you know, unusual properties of water. This is very good for thermal regulation. Because 44 kilojoules is a significant amount of energy. Just to vaporize that. All right, so this is good because do we have to worry about the work? You know, there's work involved in this, isn't there? Because we're going from liquid water to gaseous. So, you know, the volume is going to grow about 25 liters roughly. But are we going to worry about that? Not at all, because this is the net. The work has already been taken care of. So we don't have to worry about the pre-tax price. And we probably don't even care what the pre-tax price is anymore. We just want to know what the net is, right? The same thing here. Although, is there much work here? No. I mean, although ice is less dense, so the volume does expand a little bit. You know, there's a volume expansion here, and not nearly as big as this. So the work involved here is very small. Okay, let's go on to standard states and enthalpy change. We're going to look at this little superscript here. This little superscript, you know, we have subscript P, subscript B, you know, it places a restriction. This little superscript 0 places more restrictions on this. And that little superscript 0 means standard state. And this is thermodynamic standard state, which I've talked about a number of times. But this is the standard enthalpy of reaction or formation or fusion or whatever reaction or process we're dealing with. This is the standard enthalpy change for that. And it just means that the reactants and products are in their standard states. Now, what is a standard state? The standard state is the reactants or products, which could be element or compound, you know, this, at a pressure of 1 bar and at a temperature of interest. And so there's no standard temperature. You know, the temperature is whatever temperature is of interest. There's one thing missing on this slide, and that is a pressure of 1 bar or 1 atmosphere, because there's still holdouts in the US which will use atmospheres instead of bars. In fact, we probably still are dominantly atmosphere versus bar. I think many more people use atmospheres than bars in the US. And so standard state represents either 1 bar or 1 atmosphere, depends. Talk to Europe will be, Canada will be 1 bar. And there's one thing missing here. Do you know what's missing? I mentioned this a long time ago, but I don't know if it registered into your long-term memory. But standard thermodynamic is not STP. Standard thermodynamic means 1 bar, 1 atmosphere, and room temperature. It doesn't have to be room temperature. They don't, you know why? Because they don't want to fix, you know, all reactions don't happen at room temperature. There are many reactions you have to heat up, and since we have to heat those reactions up, they don't want to restrict the temperature to room temperature, you know, because in fact, a lot of people play with different temperatures to get reactions to go the way they want. And so temperature, this is very important. There is no standard temperature, but there is a common temperature. Otherwise, we'd have to have tables and tables and tables upon tables at different temperatures. But we don't want that. And so the most common temperature we use is room temperature. Not 0 degrees C. Room temperature is the most common temperature. Room temperature being 298. And so that's most common temperature of interest. Now, if you're at a different temperature, then you have to look for tables of data at different temperatures, you know. But there is one thing missing here on slide number, actually, sorry, this is slide number 39. What was the previous slide? Slide was number 37. Number 37 was missing number 2, remember that? So make a note of that. Slide number 39 is missing something, 2. What is it missing? Well, it's missing the other standard condition. The other standard condition is that the solutions have to be at what we call 1 or unit activity, which is essentially, and I'm going to talk about this later, 1 molar. The solutions need to be at 1 molar concentrations. And so the pressures at 1 bar, the solutions are at 1 molar. That's the standard state. And that's what's missing from slide number 39. Okay. And then we have enthalpy diagrams are going to be more useful. You know, enthalpy is equal to, let's say the enthalpy initials, which is down here. What is enthalpy, the absolute enthalpy, HI, equal to? HI is equal to, you know, this plot's enthalpy. What is enthalpy? enthalpy's going up here. And so tell me what enthalpy is. We talked about this Thursday a little bit, but what is enthalpy? HI, not delta H, HI. I'm here at this level, HI. And I'm going to end up here at this level, HF. And so what is HI? What is the y-axis? What is enthalpy? Well, I don't want the change. I just want what is the enthalpy, not the change in the enthalpy. I don't want delta H. I just want you to tell me what H is. H is being plotted on the y-axis. And delta H is the difference in the enthalpy here and the enthalpy here. Delta H is H final minus H initial, although we never calculate H final and H initial. But what is H? H is what we call the absolute enthalpy, not delta H, H. I want to know what H is. Delta H is equal to H final minus H initial. What is H? What is enthalpy? Enthalpy is increasing on the y-axis. What the heck is increasing? And so tell me what enthalpy is. Internal energy and not P delta V, PV. It's an internal energy, U. So this is a U initial. Well, H initial is equal to U initial, the total energy plus the PV initial. PV initial is also energy too. It's the energy state, you know, the pressure volume energy state. Why do we need the pressure volume? We've got to see if the pressure volume energy state changes. And so, you know, H final is equal to, I had this written up the other day. I was hoping to just skip it. I had time. And so basically it's the total energy plus the PV energy state. The PV energy state is going to tell us how, you know, energy is exchanged with the surroundings doing P delta V work, right? And so basically the enthalpy is just the total energy, right? It's the total energy, but what's the difference between H and U then? Isn't U the total energy? So what's the difference between H and U? Well, U doesn't factor in the work being exchanged with the system, between the system and the surroundings, right? U is just the total energy change of the system itself. But anyway, this is what we want. We want to deal with enthalpy diagrams rather than internal energy diagrams, U diagrams, because this, you know, factors in the work. We don't have to care about it. And so this is the net energy we have to input. The blue arrows, we have to put in this much energy, right? Whether, you know, work is done by the system or work is done by the surroundings, it doesn't matter, because that's the amount of energy we're going to do at constant pressure. Now, if you did this reaction in a bomb, are you going to input the same amount of energy? Not necessarily. You know, it might be, it might not be. 4 out of the 6 cases we discussed the other day, it won't be. You know, two of the 6 will be. And so if you do this in a bomb, oh, now we got to care, right? But since we do most of our reactions under constant pressure conditions, then enthalpy diagrams are more handy to use than internal energy diagrams. And so it would be better to use H diagrams and delta H rather than U diagrams and delta U, because most reactions are constant pressure, so this will be for most reactions. However, once in a while you'll do a reaction in a bomb. If you do a reaction in a bomb, is this going to be the right amount of energy? No, and then we have to make a correction. Does that make sense? And so, would be better. Now, it depends. You know, how do we determine delta H? Well, delta H we do using coffee cup calorimetry, because coffee cup calorimetry is at a constant pressure. But there are some reactions you cannot do it in a coffee cup, right? Or, you know, something similar. You know, in a regular thermo lab, they wouldn't use coffee cups. They'd use better containers than a coffee cup. But there are some reactions that don't lend themselves to doing out in the open lab, and that is combustion reactions. So there we use delta U. But anyway, we're interested in delta H. So what are all the ways of determining delta H? One is coffee cup calorimetry. Right? Two is bomb calorimetry and determining delta U. Right? Actually, maybe I need to write this down. So basically, we want to know delta H because delta H is going to tell us, and so one, of course, coffee cup, or actually, I don't want to call it. I'm going to call it constant pressure calorimetry, constant P calorimetry. Constant pressure calorimetry is going to give us QP, which we can get delta H. Delta H is equal to Q divided by the amount, QP divided by the amount. Two, we could do constant volume calorimetry. Constant volume calorimetry is not going to give us QP, it's going to give us what? It's going to give us QB. Well, QB would be like delta U, right? And then from delta U, we could get delta H, because delta H is equal to delta U minus W. So what we do is we pretend that the reaction, obviously the reaction here happens in a bomb, but we're going to pretend as if we did it in the open lab, we would calculate how much the work is. And so by calculation, done in constant pressure conditions. And so what we'll do is we'll just do a paper experiment. Okay, yeah, this was burned in a bomb, but if you did this out in the open lab, this would be the volume change, and then calculate, which we did on Thursday. We did that calculation on Thursday. But both of these involve calorimetry. Calorimetry is this basic a lot of work. Are there other ways of getting delta H without doing calorimetry? And fortunately, there are. And so we'll talk about these ways here. The first way of determining delta H without actually having to do an experiment is called Hess's law. So this is it. 3. Okay, so these 1 and 2 require experiments. 3 does not. 3 just, we look at the data in the book. So Hess's law. Hess's law, just takes some advantage of some of the characteristics of energy. One, energy is an extensive property. If you double the amount of methane you burn, you should double the amount of heat you get, right? If you triple the amount of methane, you triple the heat. That's an extensive property. And so here, if we cut it in half, let's say, I don't know why it's doing this here. Kilojoules is usually the way it's written, but this would be okay. Kilojoules per mole of N2, kilojoules per mole of O2, and kilojoules per mole of, not per mole, but per 2 moles of NO. And so if we double this, we get twice as much heat. That is, if we go with 2 moles of N2, 2 moles of O2 to form 4 moles of NO. If we cut it in half, we'll get half as much heat. So we'll go half a mole of N2, half a mole of O2. To get 1 mole of NO, we're going to get half as much heat, as you can see here. And so, in other words, we can come up. N times the reaction is equal to N times the energy. Whatever N is, the fraction greater than 1 or less than 1. It need not be an integer. Now, delta H changes the sign when it's reversed because these are state functions. So one way you go up, that's going to cost you the energy. If you go reverse that, it's going to release energy. So if we reverse this reaction, it's going to release the same amount of energy. Energy is neither created nor destroyed. And so delta H changes sign when a process is reversed. So one way we absorb, the other way we're going to release. So, in other words, delta H of the reverse reaction is equal to minus delta H of the forward reaction. In other words, just the opposite sign. And so this is Hess's law in action. Hess's law in action is this. The sum of the steps is equal to the net reaction. So what you can do here is, let's say one of these steps is unknown. Actually,
neither of these steps. Both of these steps are known here. So we have different reactions here. This 90.25 corresponds to taking a half mole of N2 plus a full mole of O2 to form 1 mole of NO and a half mole of O2. And so that's going to cost us 90.25 kilojoules to go from this to this. Okay, now if we start with this to form 1 NO2 here, so an NO plus an half NO2 gives us an NO2, that releases 5707. And now if the NO2 decomposes into 1/2 N2 plus an O2, that's going to release another 33.18. And so the step up, we're accomplishing in 2 steps down. And so in other words, the sum of the steps here, there are different ways of doing this. But we can get this reaction here. This reaction here, actually, if this was unknown, we could figure it out because the gap here between this state and this state would be 3318. And so if this arrow were pointed down, we'd be negative 3318. So negative 3318 plus a minus 5707 would give us a negative 90.25. And so this is positive 92.25, and this huge step down would be negative 90.25, the exact same. Okay, except this is being accomplished in 2 steps. So the sum of the 2 steps is equal to the net. We'll look at it again in a process like this. So let's say we're after this reaction here. If we're after this reaction, let's say a half an N2 plus an O2 yields NO2, and we know the data for this. Let's say this is unknown. Actually, I don't know it. Then what we could do here is we could see if we could add these 2 to get this. So if a process occurs in stages or steps, even hypothetically, the enthalpy change for the overall process is the sum of the enthalpy changes for the individual steps. This is Hess's law. And so let's see that in equation form here. Actually, let's do Hess's law. Hess's law is very similar to it's still loading. Wow. It's still loading. So let me switch over to this. So basically with Hess's law, we need some kind of database of reactions. And so database or given reactions, in this case, we could see in the homework here. So here's a reaction. Well, one thing we could do is we want to determine delta H for this reaction. So if we want to determine delta H for this reaction under standard condition, then the gases have to be at 1 bar. Liquids, we don't care. But solution should be at 1 molar. These are just pure liquids here, so we're okay. So we got 1 mole of CS2, 3 moles of Cl2, 1 mole of CCl4, 1 mole of S2Cl2. So we want the delta H of this reaction. Well, we could do this in a bomb. Try this in the coffee cup. But those both involve calorimetry, right? And calorimetry is quite a lot of work. And so if we have some known reactions, and so this would be the database of reactions here. Let's take a look. Here's some known reactions. In fact, give us a whole bunch of them. There's 1, 2, 3, 4, 5, 6, 7 reactions here that they're giving us that maybe we can some way add these, in some combination to get the net reaction. Now, actually, it's the strategy for this is pretty straightforward, but sometimes adding these things up kind of gets complicated. And what you end up doing is you end up making mistakes and having to go back and fix them. But you know, the strategy is simple enough that if you have enough time, you'll get the right answer. Even if you get stuck, you know, you just back up and try something else. And so what we're after is 1 mole of CS2, 3 moles of Cl2, gas, CCl4, carbon tetrachloride liquid, plus S2Cl2 liquid. This is a redox reaction here. And so that's what we're after. And this is the strategy that we use. The strategy that we use is this. Okay, we look at all these reactions here, and when we go, okay, what do we want? We want 1 mole of CS2. Do any of these have CS2 on the left? The first one does. It's convenient. Do any of these have CS2 on the right? None of them. Because one thing we could do is we could just flip the reaction backwards. There's no problem with that. We just change the sign. Do that. But you know what? This first reaction has CS2 on the left. I don't care about the other stuff because all I care about is 1 mole of CS2, right? And so what I'm going to do is I'm going to take reaction 1 and then just use it as is. And so reaction 1 is CS2 plus 3O2 yields CO2 plus 2SO2. Well, what about all this other junk? I don't worry about all that other junk. You don't have to worry about all that other junk because if you do this right, it'll work out. Okay, then I need 3 moles of Cl2. Do any of these reactions have Cl2? Yeah, actually 3 of these reactions have Cl2. Do you see that? Reaction number 2, reaction number 3, and reaction number 5 have Cl2 on the left, and then over here none of these have Cl2 on the right. And so which one should I use? Should I use reaction number 2, or should I use 3 or 5? Why 2?
Because there's S2Cl2 in the products.
S2Cl2, but how many moles do I need? Because I only want 1 S2Cl2 in the product. So here is, we have 3 choices, right? Sometimes all 3 will work, you know, sometimes not. And so what you do is you just try one, and if it fails, try another one, you know? And we could use this one, but you know what? I'm not going to use this one because this one is going to, because I need 3 moles of Cl2. And so I'll have to multiply this by 3, which gives me 3 moles of S2Cl2. Well, if I get 3 moles of S2Cl2, I got to get rid of 2 of those. So you know what? I don't want to use that one because it's going to complicate things by. But then, you know, but it's likely it could work fine. You know which one I'm going to use? Let's see if I use this one. If I use this one, that's going to screw up this. That will take the CCl4 as well, right? I'm going to use this one. You know why I'm going to use this one? Because this one is not going to mess up any of these others. That's why. Maybe it's a trick. Maybe they want us to use the first one because... No. Probably it's not a trick. I'm going to use this one. I'm just going to multiply by 3. If I multiply this by 3, what do I have to do to delta HR? Multiply by 3. And so I'm going to use 3 times reaction 5. And so this is delta H1. So CS2, if I multiply that one by 3, I'm going to get 3 SO2s plus 3 Cl2s yields 3 SO2Cl2. And I'll just do 3 times delta H5. Oops. Yeah, I'm going to turn this on. All right, now what do I have? I have 1 mole of CS2. and 3 moles of Cl2. That's what I want, right? And what do I want as product? I want 1 mole of CCl4. What has 1 mole of CCl4? Okay, it's this one. I only have one choice here, right? And so I'm going to use this one as is. And that is reaction 3. So reaction 3 is carbon solid plus 2 Cl2 yields, oops, got to twist this over, plus 2 Cl2s yields CCl4. Okay, this is reaction 3. And that gives me 1 mole of CCl4, and then I'm only missing one thing. What is that? I'm just missing S2 Cl2. And so I need just 1 mole of that. And so I'm going to use reaction 2. That's 2 sulfurs plus Cl2 yields S2Cl2. And this is reaction 2. Actually, I need this. Delta H3, delta H2. Gives me that. All right, now hopefully if we did all this, everything else cancels out. Let's see. And so what I'm going to do is I'm just going to add everything up. When I add everything up, did everything else cancel out? Did anything cancel out? And let's take a look. Well, some stuff did cancel out. And so if I take a look at this, let's see. I have 2 SO2s here. I have 3 SO2s here. And so let's cancel those out. That leaves me with 1 SO2 here. Did anything else cancel out? No. No. Doesn't look like it. And so I got to get rid of some more stuff. What else? I got to get rid of the O2. I got to get rid of the CO2. I got to get rid of the SO2Cl2. Let's get rid of the SO2Cl2 first. How do I get rid of that? Well, let's see. I use this one for the chlorine, but you know what? I'm going to have to screw that up. The chlorine's already screwed up, if you can see. And so, do you see the SO2Cl2? Let's get rid of that. So I got 3 SO2Cl2s I got to get rid of. Is that correct? Yeah. And so, you know what? I got to reverse this one. Maybe I used the wrong one here. You know, what do you think? Yeah, because if I reverse this, then I'm going to be adding 3 of these and then subtracting 3 of these. Do you see that? And so maybe I don't want to do that. Maybe I want to use a different one for the chlorine. And so let's do this. Should I go ahead and erase this, or should I go ahead and subtract it out? Let's erase this. I made a mistake here. And that means that doesn't cancel out there. Actually, let's stop here and see what we got. If I stop here, look at, I have 3 chlorines there. 2 and 1, that already adds up. And so what I need to get rid of the CO2, the O2, the carbon, the sulfur, and the S2Cl2. Oh, no, I need that. So I want to get rid of the CO2. How can I get rid of the CO2? Which reaction? Well, we have 2 choices. Do you see the 2 choices? Did I screw up the count? Shoot, I might have screwed up the count. This is reaction 1. Yeah, I screwed it up. Oh, no, I didn't. That's right. All right, so I could use this one to get rid of the CO2, or I could use this one to get rid of the CO2. Which one's better? the sixth one, because if I use this one, I'm going to screw up the other things. Do you see that? And so I'll use this one to get rid of the CO2. And in order to use this one to get rid of the CO2, I want to get rid of CO2 on the product side, so I got to make this CO2 on the reactant side. So all I'm going to do is I'm going to flip this one backwards. If I flip this backwards, I need to change the sign to positive. So let's go ahead and do that. This is going to be the reverse of reaction 6. Is that right? Reverse reaction 6, I'm going to get CO2 goes to C plus O2, and this would be a negative delta H of 6. All right, so now let's see where we stand here. The CO2s cancel. Carbons cancel. And one of the O2s cancel. That leaves me with 2 O2s here. Seems we're getting a little bit closer here. But I got to get rid of this SO2. How am I going to get rid of the SO2 and the remaining O2s here? Yeah. I need to get rid of 2 SO2s. So let's take 4 and reverse it, and then multiply by 2. And so I'm going to get reverse reaction 4 times 2. And so we're going to have 2 SO2s goes to 2S plus 2 O2s. Now that gets rid of the 2 SO2s, that's good. Oh, it also gets rid of the 2 S's, that's good. And it also gets rid of the 2 O2s. And we're left with what we need, what we want. Okay? And so when we add all those up, what do we get? Well, when we add those up, we get CS2 plus 2 Cl2s, and 1 Cl2 gives us 3 Cl2s. This goes to CCl4 plus S2Cl2. Now delta H for this reaction is equal to, if I did everything right, we just add up the steps. So Hess's law says the delta H for the reaction is equal to the sum of the delta H's for the individual steps. And so let's go ahead and sum those up. We got delta H1 plus delta H3 plus delta H2 minus delta H6, or plus or minus delta H6. And then this last one, which is the reverse of 4 times 2. So minus 2 times delta H4. Plus a minus 2 times delta H4. And so just put in the numbers. You know, delta H1 is minus 1077 kilojoules per mole. I'm going to put the units at the end. Delta H3 is minus 135.4, so plus or minus 135.4. Delta H2 is minus 58.2, so plus or minus 58.2. Delta H6, we got to reverse the sign, so 36 is plus 393.5. And 2 times delta H4 would be 2 times 296, which would be what, 580, 592, 593.6. 593.6. And we have to change the signs, so we leave it like that. Okay, and then just add them up. That's Hess's law. So Hess's law, even though that was quite a bit of work, that quite a bit of work is easier than doing calorimetry experiment, right? So, any questions on Hess's law? Now, this is whatever reactions they have. You know, somebody had to do some calorimetry, right? Or somebody had to do a lot of Hess's law to get this database of reactions. Well, there's a huge database of reactions that we can use. But the thing that makes it a heck of a lot easier is, do you know we had to do a lot of trial and error. The thing that makes it a lot easier is if we only use a specific reaction type. If all the reactions are what we call a formation reaction, then we don't have to sit there and cancel things out. Because in a formation reaction, we have the substance of interest, right? But everything else will cancel out naturally. The reason everything else cancels out naturally is because, what the heck? Put it here. I lost the projector. Could not connect. Wow, I decided to switch to PowerPoint today, and projector fails. I'm stuck on laptop. Oh, no, I connected now. Okay, regain communication. All right, so if we restrict this to one type of reaction, let's go back to this one, then this becomes so much easier. You know, this was a bit of a pain, but Hess's law with something called a formation reaction. Formation reactions can always be recognized. They'll have a little F here. And so if you see this, this is for a formation reaction. Now, formation reactions are easy to recognize because the way they're defined. A formation reaction is a formation of 1 mole, underline 1 mole here. You guys saw I posted these on Piazza, right? Okay. 1 mole here, that's critical. Formation of 1 mole, oops, of a substance. It could be an element or a compound in the standard state. Standard state in this context means, you know, under normal conditions, let's say 298 Kelvin in 1 bar, what is the standard state of H2O? Is it solid, liquid, or gas? H2O normally is a liquid. And so this is what they mean by standard state, H2O liquid. But in this case, in the standard state from the reference forms of the elements in their standard state. And so, in other words, we're going to form 1 mole of substance from the elements in their standard state at the desired temperature. And so what this means is, and you can memorize this, the standard enthalpy of formation is 0 for a pure element in its reference form. Well, that just makes complete sense if you know what it is. And so let's look at delta H of formation of O2 gas. Delta H of formation of O2 gas is the formation of 1 mole of O2 gas, right? 1 mole. We don't write 1 here though. So let me write invisible 1 here. 1 mole of O2 gas from its elements in their standard form. Well, what's the element oxygen in its standard form? The element oxygen in the standard form is O2 gas. And so we're going from O2 gas to O2 gas. Is there going to be any energy change? This is at 298 Kelvin. So we start off at O2 gas at 298 Kelvin. We end up at O2 gas at 298 Kelvin. Is there any enthalpy change? No. And so delta H of formation is 0. And so that's what this means, because all of them are going to be similar to this. However, this is not. The standard enthalpy of formation, delta H of formation, they forgot the F here. And they forgot the little superscript here. You can add that in. This is slide number 45. Or just write it down. Delta H sub F superscript 0 is 1.9 kilojoules per mole for diamond. And the reason is because diamond is not the standard state of carbon. The standard state of carbon is graphite. And so if we form 1 mole of diamond from 1 mole of graphite, it's going to cost us 1.9 kilojoules. Well, you think 1.9 kilojoules, man, I used that to heat up my coffee this morning. Should be easy, right? Should be easy. Well, that's the energy. That's the energy input. They aren't talking about the path. The path for this is very difficult, right? Delta H is a state function, so unfortunately you can't convert graphite into diamond just by inputting the amount of heat you added to warm up a cup of coffee. Otherwise, I guess they wouldn't be so valuable. Although, you know, synthetic diamonds are being produced cheaply nowadays. So anyway, here's some graphite, here's some diamond. The path in going from graphite to diamond is a bit complicated, but the energy is just there. It's 1.9 kilojoules. Bromine. Bromine is normally a liquid. And so to form bromine gas is going to cost you energy because you got to vaporize it. You know, vaporizing it means evaporating or boiling it or whatever. And so it's going to cost you 31 kilojoules roughly. And let's look at some values here. But you know, these are what we call standard enthalpies of formation. And these are all formation. Well, what are the reactions for this? So if we look at carbon monoxide is going to cost you, or actually it doesn't cost you anything. You release this energy, 110 kilojoules. And so when you see that, there's this very specific reaction that goes with that, delta H. And so what is the reaction or process that goes with that delta H? They don't show it. The reason they don't show it is because it takes up too much room, and you're expected to know what it is. And so what it is if I have a delta H of formation, the reaction for this delta H of formation of carbon monoxide gas is equal to minus 110.5 kilojoules. Now, that is formation of 1 mole of carbon monoxide gas from the elements in their standard state. Well, the element in the standard state, carbon is graphite, and oxygen is O2. And so what we have is something like this. We have that the reaction that this delta H is for this. It's formation of 1 mole of carbon monoxide from the elements, carbon and oxygen. All these are the same thing. You know, we can pick up one more that's more complicated. Let's see what's more complicated here. Let's do this. Do you recognize this one? C2H5OH. What's that called? Ethanol. So let's do that. The standard enthalpy of formation of ethanol, C2H5OH, liquid, this is pure ethanol, is equal to minus 271.1 kilojoules. Well, you know, what that's going to be is we're going to form 1 mole of ethanol, C2H5OH, from the elements. And so we need carbon, graphite. So how many moles of carbon graphite do we need? We need 2. We have 2 carbons here. And then hydrogen is H2. We need H2, we got 6 of those, so we'll need 3 H2s. And oxygen is O2, so we'll need half a mole of O2 to keep things balanced. And both of these are gases under normal conditions. And so this would be the reaction. But you know, to write out the reactions is not necessary because as long as you know the definition, it's easy. And it takes up a lot less space to have here. And so let's take a look at these in Appendix D. If we go to Table D2 in Appendix D, I'll show you what it looks like here. If we go to table D2 and appendix D, take a look at the first column. The first column is delta H of formation, standard enthalpy of formation. Okay, so here, let's look at the first entry here. It's aluminum. The standard enthalpy of formation for aluminum is this. We're going to form 1 mole of aluminum from aluminum. And so we go from Al solid to Al solid at 298 Kelvin. This is at 298 Kelvin, appendix D. And so you start off at 1 mole of aluminum at 298 Kelvin. You end up at 1 mole of aluminum at 298 Kelvin. What's the energy change? 0. So it's 0. In fact, all the elements are 0. Barium, solid barium, 0. Let's continue on. Beryllium, 0. Bismuth, 0. Boron, 0. Obviously, they all have to be 0. Unless, let's look at something like oxygen. Unless, you know, there are different forms of oxygen. O2 is the standard form, but there's also atomic oxygen. In order to form atomic oxygen, it's going to cost you about 249 kilojoules per mole to form atomic oxygen from regular diatomic oxygen. Ozone. In order to form ozone, it's going to cost you 142.7, because those are the non-standard forms of oxygen. Okay. Now let's take a look at some of these entries here. You know, let's look at some highs and let's look at some lows. You know, highs and low. I mean, look at minus 3441. That's a lot of energy. And so this, you know, aluminum sulfate is a lot more stable than the elements. You know, we're starting off with the elements here and then dropping down. It's a lot more stable than the elements. You see that in this slide. You know, some things will have exothermic, meaning they're more stable than the elements. Some things will be endothermic, they're less stable than the elements. Standard form. Some things will be 0, that is, they have the same stability, like all the elements. They're the same stability as themselves because they are themselves. So. Now, this table is kind of interesting because there's a couple of unusual entries. Oops, go back to the table here. So you look at the entries and you go, okay. You know, a lot of exothermic, some endothermic. Okay. But after you look at these numbers for a while, you come across something kind of strange. For example, this. This is very strange. Very, very strange. This one makes complete sense. This is not strange at all. H2 gas. The standard enthalpy of formation of H2 gas is not strange at all because we're forming H2 gas from H2 gas. So if we form H2 gas from H2 gas, what's the change in energy? 0. No problem with that. But what's the one above it? If we form H plus AQ, 1 molar is 1 molar, right? Because it's standard. We form 1 molar from 1/2 H2 gas. What's the delta H of formation for this? 0. Now, are you going to tell me that it costs no energy to break a hydrogen molecule in half? Let's say I have a 1/2 mole of hydrogen molecules. Does it cost no energy to break the bond between the two hydrogens? What would you say? No, it's going to cost you energy, right? To break apart the two hydrogens costs energy. And then you take a hydrogen and you pull off its electron. It's only got one electron. Is that going to cost you any energy? It's going to cost you energy. And then you dip it in water. Well, actually, when you put it in water, it releases energy. But there's energy involved. And this is saying there's zero energy involved in this change. What do you think? This makes total sense, right? This doesn't. Why? Why it doesn't make much sense is because it should cost you energy. I mean, or release energy. There should be some change in energy. It would be very unusual if there's no change in energy, right? That means hydrogen gas. If you have a cylinder of hydrogen gas, then you could be looking at a lot of H plus AQ in there. Does that make sense to you? This one is unusual. The reason it's unusual is this. This is not actual. This is by arbitrary definition. Someone just chose H plus to define this process as zero. Let me tell you why they chose this. Your book doesn't. Your book goes into it, but your book's PowerPoints don't go into it. Can you do a calorimetry experiment like this? Is this possible to measure using calorimetry? Get some hydrogen gas, no problem. You couldn't do this using calorimetry. Do you know why? You couldn't do this using calorimetry because if you form a cation, you must also form a anion. You cannot just form a cation alone. There's got to be somebody who loses and somebody who gains the electron. Okay. This is why, redox. If something is reduced, something must have been oxidized. And so let's take a look at ways we might be able to measure something like this. Well, one way is, you know what? This is by arbitrary definition from, I'm going to use this as an example. But it doesn't have to be this specifically. It just has to be something similar to this. And that is, let's look at the formation of HClAQ. HClAQ, is it a strong electrolyte? Yeah. That means HClAQ consists of H plus and Cl minus. I know, how many of you had to do hydronium in Chem 4? I think that's, if you had to do hydronium in Chem 4, this might screw you up because this one, because, when we think about delta H's of formation and other things like this, why do, you just take this as hydronium. And that's usually what we do. H plus is equivalent to hydronium. But do not worry about the water. I noticed some people did hydronium because the water got misbalanced. So this is why I don't do it, because in thermal, the waters will always, turn up. And then people will want to add the waters into the thermodynamic equation, but it's already factored in there. And so, anyway, doing hydronium, let me tell you, in Chem 1B, that's all you do is hydronium. You don't do H plus in Chem 1B. It's all hydronium pretty much. And so for right now, we treat this as H3O plus. And don't worry about the waters, because we aren't going to add the waters in here because it's already factored in. Water's already factored in. Here, H2O liquid. Well, anyway, how do we form this? Well, we're going to form this from the elements. So we'll take 1/2 hydrogen gas plus 1/2 Cl2 gas to get HCl. Now, well, what is HCl? Well, that's H plus and Cl minus. So we have 1/2 hydrogen gas plus 1/2 chlorine gas gives us H plus AQ plus Cl minus AQ. Now, we could do a calorimetry experiment for this. It's not hard. We do a calorimetry experiment, and we get a delta H. The delta H for this reaction is equal to minus 167. Actually, minus 167 point. Let me give you the exact number. I'm just going off the memory. 167.2 kilojoules. So this reaction is fine because we're forming a cation and we're forming an anion. Now, now what? Now I want to figure out of that 167.2 kilojoules, how much was due, how much of this total, this is the total, how much of this total was due to H plus, and how much of the total was due to Cl minus? You know, could I assume it's a 50-50? Maybe half the energy is due to a formation of H plus, half the energy is due to the formation of Cl minus. Is that fair? You might go, hey, that's not fair. I think what's fair is maybe a 30-70. Maybe 30% of the energy goes to H plus and 70% goes to Cl minus? Or do I have that backwards? Maybe it's a 70-30? Or maybe it's a 20-80? What do you think? Could we, hey, you know what? I want to redo this calorimetry experiment, but I want to get rid of the Cl. Can I just get rid of the Cl and do the calorimetry? No, because if I have a reducer, I need a oxidizer. And so I run into the problem. Well, you know, I could do this theoretically, but you know, my theoretical calculations are very difficult. So I'm not going to do it theoretically. This is going to be an error anyway. And so, you know what? This is a problem. This is a problem where this is what I call a Q unknown, X and Y, and one equation. Well, if I got two unknowns, one equation, all I have to do is think of one more equation. But there's no one more equation. Shoot. If I have two unknowns and one equation, what should I do? Now the easy answer is just give up. You know, not enough information. You didn't give me enough information to solve this problem, so just give up. But you know what? They didn't give up. You know what they did? They just went ahead and arbitrarily said, well, you know what? I'm going to call X, and I'm going to call it 0. I'm just going to call X 0. And so this is the cutoff. This is the split. 0% of the energy is due to the formation of H plus, and 100% of that energy is due to the formation of Cl. Is that right? That sounds like an idiotic thing to do because it just is totally wrong. But it isn't an idiotic thing to do. The reason it isn't an idiotic thing to do is because you always have to form an anion whenever you form a cation, right? Always. And so what this is what we call a systematic error. All the cations are going to be in systematic error one way, and all the anions are going to be in systematic error the opposite way. And when you add the cation with the anion, the negative error cancels out the positive error, and you have no error. So it turns out it wasn't an idiotic thing to do. It was a brilliant thing to do because of this. So all the cations are going to be shifted one way in error, and all the anions are shifted the other way, but we're never going to have a reaction where we only form cations. That is the oxidation part. And we're never going to have a reaction where we form anions, the reduction part. It's got to be redox. And so we're looking at three tables in here. When we look at the delta H's, all the cations are errors in one way, and all the anions are errors in the opposite. And so when we add up those two, we get the right answer. So let's do this one. We're going to do this one quickly, because I need to finish this chapter, at least today. Finish this chapter. Well, doing this one quickly, I want to figure out the delta H of formation for HCl. Well, the easiest thing is just look it up. Look it up. Delta H of formation of HCl is this, right? But I'm going to do it the Hess's law way. Now, if we only use formation reactions, if formation reactions are used, or strictly used, the only reactions used in Hess's law, then we have this very simple equation. Delta H of reaction is equal to the sum of the delta H's of formation of the products. This is what we call nu P. Minus the sum of the nu R, delta H of formation of the reactants. Okay, this nu just is a stoichiometric coefficient, how many moles of it we have. And so, to do this as an example, well, let's do delta H formation of HCl. Or actually, we don't want that. We're just going to do this reaction. 1/2 H2 gas plus 1/2 Cl2 gas yields HClAQ. This is a formation reaction because we're forming it from the substances in the standard state, so I could just look this up. But if I'm going to apply this, I'd say delta H for this reaction is equal to the formation of the product minus the formation of the reactant. And so the formation of the product well, I want to do it this way. I'm going to go H plus plus Cl minus. Actually, we've got both of them. So using this second one, actually we have variations. We can do it first one too, because I got delta H formation of HClAQ right here. But I'm interested in H plus and AQ. So this is going to be the sum of the delta H's formation of the products. So I have 1 mole of H plus, 1 molar concentration, times delta H of formation of H plus. What is delta H of formation of H plus? Look that up. Delta H of formation of H plus is 0. That's the first term, the product. Plus 1 mole of Cl minus times the delta H of formation of Cl minus. Well, what's the delta H of formation of Cl minus? So I go to C for chlorine, and then look. Book. Do you see it? Cl minus AQ, delta H of formation is minus 167.2. Okay, so far I have 0 plus a minus 167.2 kilojoules. Okay, minus the delta H of formation of the reactant. Well, delta H of formation of hydrogen is 0, and delta H of formation of chlorine is 0. So 1/2 times 0 is 0, 1/2 times 0 is 0. So this is 0, which gives me minus 167.2 kilojoules. Now take a look at this. Cl minus AQ is minus 167.2. Now I told you there was another way we could have done it. We could have just gone straight to HCl AQ. If I went straight to HCl AQ, what is the delta H of formation of HCl AQ? The same thing. It's minus 167.2. And so that's just it. And so, in other words, yeah, we had this two unknown, one equation problem, but we fixed it. We fixed it by doing what's called an arbitrary zero. Okay, arbitrary zero. So you should know that. And so all the cations are in error one direction, all the anions are in error in the opposite direction. We just add them up. And so let's do another example of ions in solution. Now, I know the Cl minus, but what about some other things? Okay, well, let's take a look at some other things here. Let's look at a reaction here. As an example, magnesium solid plus 2 HCl cubed. We're going to yield, do I have magnesium chloride or do I have magnesium ions and chloride ions? I got magnesium ions and chloride ions. Yields magnesium chloride, AQ plus H2 gas. All right, I want to figure out what the delta H for this reaction is. Well, what I'm going to do is I'm just going to use the Hess's law with formation reactions. That would be the easiest. So let's try that. All right, so that means I have 1 mole of magnesium chloride, that's my mu, times delta H of formation for magnesium chloride AQ. Plus 1 mole of hydrogen, 1 mole of H2, times delta H of formation for H2, minus the reactants, minus 1 mole of magnesium solid times delta H of formation for magnesium solid, plus 2 moles of HCl AQ times delta H of formation for HCl cubed. Well, some of these we should know right off, like hydrogen, delta H of formation of H2 gas is 0. Magnesium, 0. And so this is it then. So let's just look. I know this one, delta H of formation of HCl. Minus 167.2 kilojoules per mole times 2 moles, so I got to double it. And then I just got to find MgCl2. So let's go to MgCl2. MgCl2 is minus 641.3. Is that right? Minus 641.3. No. Because it's a state. That's MgCl2 solid. You know what? I don't have MgCl2 aqueous. So does that mean I can't complete this problem?
You break it down.
Yeah, I'd have to break it down because I know MgCl2 is a strong electrolyte. And so actually MgCl2 consists of Mg2 plus 2Cl minus AQ. then I could figure it out. And so what I'm going to have to do is I'm going to have to change this. This, I can't use this, unfortunately, so I'm going to have to break this down. I'm going to form 1 mole of magnesium 2+ ions times the, well, I got it here, delta H of formation of magnesium 2+. So delta H formation of Mg2+, which is minus 466.9. And then 2 moles of Cl minus. This is going to be plus 2 moles of Cl minus. Well, I remember what delta H formation for that is. Delta H formation for Cl minus is 167.2, negative 167.2. So actually, you know what? These two cancel out. And then it's just the delta H for this reaction comes out to minus 466.9 kilojoules. Okay. So that's the easiest way of determining delta H's, for sure. And so once we determine delta H's, then how can we use them? Well, we can use them to predict, how much energy is it going to cost or how much energy it's going to consume. And so let's take a look at that. Here's a breakdown here. Oops. Show this here. Here's a breakdown here, but we don't have to draw diagrams like this. We don't have to add up the individual equations. All we do is just take the products minus the reactants. So the equation shown at the top, and this is what we have. This is what we have happening. We just ignore those enthalpy diagrams, basically, and just focus on this equation at the top here, which is much easier. This is dealing with ions. We just treat the ions like we just did here. Here are some ions. The cations are in error one way, the anions are in the error in the opposite direction. Okay, we'll apply. Now, how do we apply this? We apply this for figuring out how much energy it's going to yield. So here are some enthalpies of combustion. Municipal waste gives 12.7 kilojoules per gram burn. We look isooctane, 47.8. Natural gas, 49.5. So on a per gram basis, it looks like natural gas gives the most. But it's a gas. Gases don't weigh much. And so even though this gives a lot of heat per gram, it's not very concentrated. It's natural gas. So we could use, once we figure out the delta H's, we could use it. So if I had a ton of natural gas, how much heat am I going to get? Well, I could do a calculation using this as a conversion factor here. Energy consumption by source. This is BTU. BTU is British thermal unit. I gave one homework problem on BTUs, although I haven't really talked about it. Greenhouse effect. Greenhouse effect is, greenhouse effect is what happens with vibrational energy. What happens is, the Earth absorbs this sunlight, and then it's radiated off heat. And this heat is captured by things that vibrate nicely, like CO2 vibrates nicely. N2, O2, they vibrate too, but those aren't considered greenhouse gases because they don't absorb infrared oddly enough. The greenhouse we'll talk about later. Other sources of energy. It's not. All right, what we're calculating here in terms of this driving force is, typically, actually there's biological sources. We're going to do an example. Since I don't have enough time to do an example today, we'll do it tomorrow. But typically in nature, things go from higher energy to lower energy like that. We call that spontaneous. So this would be spontaneous, right? But this would be non-spontaneous. If the pen were to jump back into my hand, that would be non-spontaneous. But for the most part, chemical reactions, delta H exothermic is spontaneous. And so if we have a delta H that's exothermic, it's spontaneous. However, in chemistry, sometimes endothermic reactions are actually spontaneous. And so we'll talk about that tomorrow. Tomorrow we're starting a new lab. You don't have to prepare for tomorrow's lab. Tomorrow's lab is chapter 8. And so we'll start chapter 8. Start talking about chapter 8 tomorrow.
I'll see you tomorrow. Okay.